So this is the stress strain diagram of a mild steel. So initial slope is called modulus of elasticity. This is modulus of elasticity. Now it is the initial slope. That means if I consider only, okay, take another color. If I take the very initial portion, this is point number 2, this is point number 1, then what will happen? So sigma minus 0, epsilon minus 0, or sigma divided by epsilon. So stress by strain is called modulus of elasticity. Now where you got it? It is also called Hooke's law. Yes, scientist Hooke's, he told us at the very beginning our stress is proportional to strain. At the very beginning, if our load is very small, then stress will be proportional to uh, strain. That means it will be linear. So proportional means actually linear. If I use a very plain language, or I can write this way: stress equals E times epsilon. This E is called proportional constant or modulus of elasticity. Or we can rewrite this equation into this format. You can see E will be stress divided by strain. Or I can write whatever I need. Based on the need, I can write this way also. Also based on the need, I can write stress is E times epsilon. So make sure that you are familiar with this equation, these three equations. Something else to tell you. Whatever equations are easier, that is more useful. So if an equation is so big, we do not use it very often. If equation is very small, we use a lot. So this is the one of the easiest equation in civil engineering. In civil engineering, three equations are very important, and those three equations are very easy. One equation is this. Second equation is force equals F equals ma, or weight equals m times g. This equation is force equals mass times acceleration. Very easy equation, but we use a lot. Third equation we use is Q equals CIA. It is in hydrology class, the discharge. Okay, I'm not going there, but very shortly, that these three equations very easy, but we use a lot in civil engineering. Okay, forget this now. So this equation very easy, but very important. Okay, now if you see this equation, or whatever equation, everything is one dimensional. So if I pull something like this, it's one dimensional, one dimensional. Now if I okay, I will erase this slide before erasing. If my body is three-dimensional or two-dimensional, that means now every every member is three-dimensional. But if my length is so big and my width is so small, we can neglect one. Say our road, is it one dimensional or three dimensional? Obviously it is three, but the length is so long, 1,000 miles, 2,000 miles, and my width is only 20 feet, 30, 40, 50 feet. So in that case, we consider only one dimensional. A cable, it is obviously three dimensional, but the length is so big and the thickness is so small, we neglect one side. So if in that case, so before starting that case, let us do a case. So if it is a three-dimensional body, if I pull and at the same time if I push here, then oh sorry, it will be like this. I should not use this portion. So if I pull at the same time if I push laterally, then my increase in length will be even larger. If I do not apply this one, only my pulling, then my strain will be um, sigma divided by E. It is only one dimensional. But if we do at the same time, if we push laterally, that means somebody else is helping me. So then you okay, you can see this portion is tension and this portion is compression. So the equation is like, if it is multi-dimensional, then we can write this way. Say sigma x. Our equation was, oh, epsilon x equals sigma x divided by E. Now, other question, should I write Ex? It depends, like most other term is called isotropic. Isotropic. What does isotropic means? Isotropic means my modulus in any direction is same. My modulus in any direction is same. That is called isotropic. Commonly we use isotropic assumption, and steel is isotropic. Concrete is isotropic. We can assume that. Soil, we can assume isotropic. But again, it's not perfectly isotropic. Say asphalt, concrete. Is it isotropic? So my road is this. When my wheel is going, is my asphalt here? The modulus this way and modulus this way, is it same? Never same. Why? When you compact, we compact only one way. We compact only one way. We do not compact both way. So in one way, it is higher, y will be less. Common sense. But in concrete, even when you compact, but we in concrete we vibrate. As we vibrate, we can assume that it is getting compacted all directions same way. So in concrete we use this. So that is the meaning of isotropic. In undergraduate we always assume isotropic. So I will not write Ex. E. Any direction E. Now, if I say this is my x direction, this is my y direction. Y direction. Oh, why I wrote minus. Then if I apply both x and y, my Ex will be sigma x minus divided by E minus Poisson ratio sigma y divided by E. Or simply we can, oh, now how I wrote this equation? It is the same equation. But why it is Poisson ratio? The reason is we are considering the longitudinal sigma x, longitudinal. We are taking the effect of transverse. So what is the connection between longitudinal and transverse? That is the Poisson ratio. We learned it. Poisson ratio is lateral strain divided by axial strain. So that is why. Now I can simply write this way: sigma x minus sigma y. That's it. Now in this case, in this figure, you can, if sigma x is positive, sigma y is here, sigma y is negative. Why? Because if we assume tension positive, compression will be negative. Now if we use sigma y negative, you can see if we use this term negative, and then here it will be ultimately positive. It will be positive here. Then you can see my sigma x will be, sorry, epsilon x will be higher. So if you pull a body at the same time, if you push laterally, your deformation will be higher. It makes sense. But you can see here, if you pull this way at the same time, if you pull this way, my change in deformation will be lower, because whatever it is going this way, this portion will pulling that way, so it will be lower. So in that case, this sign both are positive. That means this is positive, and ultimately this will be negative. So my equation and my real life is matching. Okay, same way, if it is three-dimensional, we can write this equation that way: sigma x minus mu sigma y sigma z. So hopefully you learn this equation, whatever equation in your book. Hopefully you, in this body I wrote three equation. Do not get nervous, do not get upset. It is that same equation. When I am taking sigma y, sigma y here, sigma x and sigma z here. When I am taking sigma z, sigma oh, I'm making mistake, epsilon z, sigma z here, sigma x and sigma y, they are here. And sigma means stress, epsilon means strain. So you, yeah, I hope that you understood this equation, and nothing to memorize. It is in your book, in your AP exam. In your AP exam, these equations are given, so no need to worry about it. Just concern about the direction, concern about the sign. If you assume tension positive, compression will be negative. Sign convention up to you. Oh, this example, I think we solved last class. It is how to calculate Poisson ratio. Oh, maybe I'm talking so much and you are getting bored. So I'll go to problem very quickly. Yeah, this one is the how to calculate modulus of elasticity. We know that modulus of elasticity is stress over strain, and they calculated axial stress, they calculated axial strain, and you can see they took original dimension, because by stress strain we mean the engineering. So always take the original, unless the problem tells you true stress or true strain. But I believe problem will not tell it, because we do not use true stress, true strain in our engineering. Okay, so I do not need to explain this problem. It's very simple. Force by original area is stress. Change in deformation divided by original dimension is strain. You can take the fraction or you can take the percentage. Oh, actually, for elasticity, you should take the fraction. I do not know why I use percentage here. Uh, Percentage was like when we used Poisson ratio that time. I know why I use this, because when I used that solved that problem, I copied and pasted, and then it became that mistake. Okay, so this problem is change in diameter after applying a tensile force. Yes, something different. So what is it is asking? Change in diameter. If I go to not here, what I did. If I go here, mm, change in diameter. Can you remember when we use change in diameter? It is lateral strain divided by axial strain. So lateral strain is mu times axial strain. Or simpler, I do not need to use this equation. Lateral strain is delta D divided by original diameter. So change in diameter will be epsilon T times D naught. So if you know D naught, if you can find epsilon T, you are done. Now question is, do you know epsilon T or no? Maybe you do not know, no problem. So in that case, what you can do, you can also use this equation to find epsilon T. So find epsilon T from here and then plug in here, then you will get sigma D. Simple calculation. So you're understanding whatever you know, you now you are using it. Like you have some money, you have some property, now you will use this to solve your problem. That is it, yes. Okay, now how to find epsilon A? Very simple. Epsilon A is delta L divided by original dimension. Poisson ratio will be given to you. Yes, something must be given to you. You cannot find everything in the same problem unless you do the testing. Okay, let us see what they did. Yeah, they, you can see they gave you Poisson ratio. They gave you modulus of elasticity. Oh, again they gave you modulus of elasticity. Maybe I'm jumping so much. Yeah, if they gave you modulus of, actually there are many. All depends on what is the data given. So what they give us, original diameter, original length, modulus of elasticity, Poisson ratio. Calculate the change in diameter. Now, if I do not see the solution, first what I will do, I will list down all the equation. Oh, I do not know whether you wrote it down or no. Yeah, when I will delete it or close it, I will give you warning. Stop me if you did not write it down. So now I am doing it. Oh, first list down what is given. Original diameter given, original L given, P given, mu given, modulus of elasticity given. Question is asking what is delta T. Now we saw that delta D is epsilon T, epsilon T times D naught. We saw it. So we need to, our D naught is given. D naught is given. So we need to find about delta T. Now how to find delta T? We know that Poisson ratio is delta T by delta A. Now there's a negative sign. Yes, use the negative sign here. Why? That will tell you is delta T decrease in diameter or increase in diameter. That will tell you. Okay, so delta epsilon T equals mu delta A. Mu delta A. Okay, now do we know this one, epsilon A? Is anything else given? Load is given, what diameter is given, so simple, yes. Other thing we know this, modulus of elasticity is sigma A divided by epsilon A. We know that. So if we can find this, we can use it here. And E is given. So we need to calculate this one first. Can I calculate this? Yes. P divided by pi d square over 4. What is pi d square over 4? That is the cross-sectional area. So now you can see P given, D given. So P given, D given. So we can calculate epsilon A. We can calculate epsilon A. After calculating, we will insert it here. Calculate sigma A, sorry, epsilon A. After calculating, insert it here. You will get epsilon T. After you found epsilon T, you can insert it here. Then you will get your sigma T. So what can I explain? That it is not difficult. All the equation, list it down and find your path, how to navigate to the destination. That's it, nothing else. Now let us see what I did. Yeah, before going, take a pause and you will see that it's not difficult. It's very easy, just at the beginning confusing because so many parameters and you have to go from one place to another. But again, it's not that you cannot do that. If you think about it, you can do that. You can see I did not see the solution. Even this handout, I did not open this handout for last 1 year. I just opened this portion just this morning before the class. So it is not that I am memorizing it. It is not possible in engineering that you will memorize. If you memorize, you cannot memorize more than 2% of civil engineering. The rest of the 98% is all about procedure. You have to follow the steps. Okay, so I will see the solution. What I did here. First they calculated axial stress, then axial strain. Same procedure, but here they found axial stress. But my question is, how do I know I need axial stress? The system is actually, the book language is typically polished. You will not see so many going here and there. Book always says tell something polished, but in real life we need to think about this way. So that is the difference. This is how book cannot teach. Actually, book cannot teach. We use book just as a reference, but as a learning or teaching is always like practice like this. So book knew that. uh, Even when I solve this problem, if I solve this way, every example will be 2 pages long, and if it is 2 pages long, nobody will study it and nobody will like the book. So this is I made short, but system is this. If I know axial stress, I can use it here. Then I will get the axial strain, and you can see here axial stress. I found the axial strain. From axial strain, I found the lateral strain. See, then lateral strain. From lateral strain, I found the change in diameter. Actually, so whatever I showed here, that is in this handout. Excuse me. Now, if we use the negative sign, negative means change in diameter is decreasing. Yes, it is a tension test. Tension test, diameter will decrease. So hopefully you understood. Actually, my main target was to solve this problem, but I am talking a lot. But before solving this problem, let us go to another problem, a short problem first. Not this one, not this one. Yes, this problem obviously. Other problem is this problem. So three dimensional. Solve three-dimensional first because it is very short. One a cube element, vertical compressive. That means this is vertical compressive. Now compressive may be positive, may be negative, depends on you. Let us assume compressive positive, no problem. For soil, everything is compressive. For concrete, everything is not mostly compressive. For asphalt, mostly compressive. So compressive can be assumed positive. There's no problem. It depends on the assumption. Okay, so vertically it is 20. Lateral compressive stress, that means lateral is 12, 12, and all are compressive. The modulus of the material is 20,000, 23,000 ksi. Poisson ratio this. Calculate the vertical compressive strain. Again, question is asking vertical. Now, vertical means what? Does vertical means z or x or y? Actually, it's up to you. But here the figure shows vertical is z. So we will use z. And question is asking vertical compressive strain. Say we are concerned about epsilon z. What is the equation? If you can remember, it is very easy to remember. Because if it is one dimensional, sigma z equals, oh, it is not sigma, epsilon z equals sigma z divided by e. As it is three-dimensional, what we will do? Parenthesis, we will deduct the other side. That is simple way. Now let us assume compressive is oh, positive. Then sigma z is 20, mu is 0.25. This sigma x is 12. This is 12. Make sure everything is the sign is the unit is consistent. So E is KSI. This is KSI. Everything is KSI. So whatever you will get, no, obviously sigma z again sigma epsilon. Epsilon has no unit, so it should be KSI. You can see KSI divided by KSI. But if you use some parameter PSI, that will be a mistake. So make sure that your units are consistent, and then whatever you will get. If you get a positive number, that means it will elongate. If you get a negative number, that oh no, we are assuming positive is comprehension. We are assuming positive comprehension. That means compressive is positive. So if you get a positive number here, that means compressive strain, contraction. If you get a negative number, it means tensile, compressive. Okay, so hopefully you understood. Very simple. You can see very simple, but Sometimes when you see three-dimensional thing, you get confused or you get scared, not confused, scared, but nothing to scare. You see here the same equation, whatever I did here, it is the same thing. So hopefully you will learn it. Then we will go to this problem, very conceptually rigor, this one, but not difficult, conceptual. Okay, for an, maybe I'm going very fast. The reason is I'm planning to solve that big uh, problem. This is why I need to go there. So I'm solving all the short example first. This example, A36 steel rod. What is A36? A36 is just a name given by ASTM. A36 A doesn't have any specific meaning. Uh, but sometimes people call, oh, A means ASTM. No, not like this. There are B, C. So A36 is just a name given by AIC, American Institute of Steel Construction. That is a specification we use for steel design. Now that steel rod, and they already told us the yield stress of that material is 36 KSI. Has a total of 0.0011 strain if stress 55 is applied. That means when the stress is 55, the total strain is given. This value is given 0.011. Calculate the permanent strain of this material. The modulus of elasticity of any steel is 29,000. Yes, this parameter, this value is no, sorry, this statement is new to you. For any steel at room temperature, the modulus of elasticity is 29,000 KSI. You can memorize this. Now, why you can memorize? Because you will use steel for many times in your career, in your degree program. So for steel, modulus of elasticity is 29,000 KSI or 210 gigapascal. I am writing here either 29,000 KSI, not P, or 210 gigapascal. You can memorize it in SI unit or in US unit. You can memorize this for any steel. Okay, so if we solve the problem, the figure will tell you a lot. It is going this way, this way, this way, and stress is 55. You can see yield stress is 36. That means 36 roughly here. It crossed the yield stress. What does it mean? It means it is in plastic region. It crossed the yield or elastic limit. So there is some permanent. Now we saw this equation. Hooke's law. What is this equation? Now you can remember E is only valid in elastic region or proportional limit, but proportional limit and elastic limit is not same, but yes, is not same. So this is proportional limit, but if your problem does not tell you where is the proportional limit, we assume that sigma y. Even I told it in last class also that this portion is very small, that non-linear portion is very small, so most of the time we use yield point as our proportional limit, although conceptually it is not so accurate. So this problem, they did not tell us what is proportional limit, so we cannot actually know it. So we will assume yield point is our proportional limit. So if we use this equation, yield, again this equation valid only in proportional limit or only in elastic region. So if we find the stress, sorry, this strain, what is this strain? This strain is yield strain or the recoverable strain or the strain that will come back. So what is sigma? Sigma is 36,000 KSI. What is E? E is 29,000 KSI. and after this, what will we get? We will get the amount of strength that will come back. I'm writing here, come back. Now come back is not a technical term. Technical term is recoverable or elastic or resilient. That is a technical term. So whatever the value we will get here, that, so if I remove my load, it come back and come here. So that is this, it will come back, and the entire this portion will be permanent. So whatever we are getting here, the given total strength minus this is your permanent. So hopefully you understood. Now if you did not understand, just think about it. It's nothing scary, nothing difficult. Total is given. I am calculating whatever the part it will come back. Now here I showed another epsilon y. Is it a mistake? No. This portion and this portion will be equal. When a material comes back, the elastic portion comes back. So this line is always parallel to initial line. So this value are mathematically equal. So again, this is actually this is. So we calculated this one. And this portion is obviously equal to this one because that is coming back in my graph. Total minus this is your permanent. Okay, if you did not understand, take a pause and try to digest. By this time, I can drink some water, but no water here. Oh, I found some. Okay, now let us see what your handout did. I think I did the same thing. Is first I calculated the elastic. You can say I wrote here elastic or yield strength, and I told you it is the strength that will come back, and this will come back. Now, total is yield plus permanent, or permanent is total minus yield. See, very simple concept. Okay, so hopefully you understood. This is very important for your exam. So I have two problems now. At least I want to solve this problem, this example. Why I want to solve this example? Because it is the basic. It is the basic, and you need to do it in your homework and also in your laboratory. In your laboratory, in fact, whatever you will do is this example. After testing the material, you will get this data, the deformation and the load corresponding to the deformation. What does it mean? When your deformation is 0, there's no load. When we applied 2.95, we got this deformation. When we applied 5.9, we got this deformation. So actually I should write this column, this side, this column, that side. I can write it. Or I wrote this way, there is a reason. The reason is, in our laboratory, we apply load, but we read the load based on the deformation. Say every 1.001, we read the load. So when we do the test, we can do both way. One is we will apply load, we will measure the deformation, or we will apply the deformation and measure the how much load we are needing to make the deformation. So both way it is possible, and this type of name is called stress control or strain control. Okay, let me write it down. What is stress control? Stress control, that means we will apply P will be applied and delta L will be measured. Strain control is opposite. Strain control, we will apply some delta L and measure what is our That is the system. And when we use stress control, we use it for hard material, hard or stiff material. We use this testing. It is easy. Strain we use when we use soft material. For example, asphalt. Asphalt is a soft material. So in asphalt we use strain control. We apply some deformation and we measure the load. For hard material like steel, concrete is hard. We apply force and measure our deformation. So both is possible. So in our chart, if P is given or delta L is given here, no problem. Or delta L is given here, P given here, no problem. You can solve it. You can handle it actually what to do. Okay, take a pause. Make sure that you are digesting. Or yeah, when I teach this class, I get hyper. This is the most interesting class to me. Like I enjoy this class the most because it has so many things to learn, so many things to feel. You can feel what is happening. So when I teach it, I go very fast and I talk a lot. So if I go fast or talk a lot, you can stop me anytime. Okay, so what I was doing. Oh, okay. So whatever is given, do not get scared. Say if P is given and delta L is given. Uh, Obviously, your L naught will be given. Obviously, your what else? D naught will be given. So L naught typically 2 inch, but it will be given different way also. Other number is also possible. For mild steel, we use a 2 inch sample and 0.5 inch diameter. Then you can calculate your A naught. How to calculate A naught? Pi D naught square by 4. Then you will calculate your say strain. What is strain? Delta L divided by original L. That means this column divided by this column is this column. So if I take a, again nothing is carried, this column and this column, you will use these two and come here. Other is stress. What is stress? P divided by area. How you will find it? You will use this column and this column. So this column, both will give you this column. So you'll get so many number. Then draw it. Whatever you'll get. Done. Is it difficult? No way. Whatever the data is given, you will know your P force, you will know your L. Again, I'm telling strain has no unit. Strain has no unit. Delta L by L, no unit. I know that many of you will make this mistake in your MCQ quiz. This question is in your quiz. What is the strain of, sorry, unit of strain? No, nothing. So simply you are calculating sigma, you are calculating epsilon. How? Delta L given. Delta L, you measured it. L naught, original length, you know it. Stress, oh, why P naught? No, not P naught, P. By P naught it means initial, no, it will change. So you will apply it, you will apply P, you will measure delta L. But for different P, different is stress. Then just plot. You get so many points. Plot. After plotting, tell what is this, how much is this, how much this is this. So that is the lab. In your lab, you will measure P, apply P, measure delta L, make a table, draw it, find all this point, find your E, find your yield stress, find your ultimate stress, find your failure stress. That is the lab. Okay, we'll do the lab. Now we will do this example. So deformation given, load given, you can see diameter given, 2 inch given. This diameter is standard. ASTM, I forgot the name, most probably ASTM E something. What is the question? Plot the stress strain curve up to failure. That means plot everything. But stress as strain, do not do other thing. Find the proportional limit, the limit of the linear portion, yield strength. You will find a peak after the yield. Modulus of elasticity, initial slope, ultimate stage, the peak of the entire curve, the failure, the last point. So if you draw it, you can do anything you like. How to draw? Find your stress P by A. Actually, P by A not epsilon L delta L by L not. So I should write actually not. If I do not write A not, it is actually the initial area. It depends on whatever symbol I used in my handout. So you can see deformation, load, strain, deformation by original deformation. You can see this one divided by your initial 2, you'll get 0.005. And how to find stress? Load divided by area. Load is kips, area is inch square, unit is KSI. Deformation is inch, original is inch, no unit. And when you will draw, make sure in x direction it is strain, y direction is stress. So place this one first. Oh, I told you I will show you how to do it in a graph. Sorry, in Excel I will show you. But you can see after plotting, I got this number. Almost the entire path is proportional, linear. So 60 is your linear limit, 60 is your yield point, both. Non-linear portion very difficult to find non-linear. So both are 60. What is the modulus of elasticity? That take the slope. Either take this 2 point, or this 2 point, or this 2 point, or this 2 point, or this point and this point, this point and this point. Whatever 2 points you will take, you will get the same value. Then you will get the slope. What is the ultimate? Roughly here. Ultimate you need to read. 127 something. If you pick this number, it will be okay. Yes, there might be some reading error, that is okay, but roughly 127, 28, 29, whatever you read is okay. What is the failure? Is 71. I can press my cursor here, I can say 71, but you can read from here. Yes, whatever you say, 68, 9, if you read it, 69, 8, 71, 72, that is right. For reading error is okay. I do not think I should go over this. Very simple. I will just show you how to do it in Excel, because on Monday, maybe defer your due date, because on Monday, okay, I will defer the due date to Wednesday. Let us solve this problem in Excel. So this data is given. Okay, so give another. I think you cannot see because it is too small. Okay. So what is this? This is my delta L. How to write delta L? Difficult question. Symbol, you can use symbol, but if I do it, it will kill my time. But I have good amount of time. Yeah, if you use symbol, it's very easy to. Why my L is so high? P. Maybe the font. Okay, this is given. Maybe before that, let us insert some. So if I take more, I don't know why it is not working so good. No problem. So what is given? My L naught is given. What is L naught? 2 inch. Right here 2 inch to make it. What is D naught? 0.5 inch. How to find A naught? A naught is pi. What is pi? 3.1416. Oh, somebody will say what is 3.1416? Okay, is pi. Pi d square. So this is d square is square divided by 4. So this is my area. Okay, I'm writing here very inch square. Now, okay, maybe give another space. Now here what we will calculate? We'll calculate say strain. This time I'm not writing the symbol. It will take time. It will take time. Now how to find strain? Or write it because what is my time? Yes, I've some not many times, but at least okay. Symbol is strain. Where is strain? Yes, this one. Then draw stress. What is stress? Stress is sigma. Oh, my sigma is here. Sigma. It has some unit KSI. And why my font is going very weird? Okay, make this a little bigger. Okay, what is strain? Who is testing me? Anybody from class? Yes. Another student from other class. Okay, don't worry. So equal sign. What is strain? Strain is deformation divided by original length. So d. Now I can simply write 2, but I'm showing you the equation. If I write this, is done. Then if I scroll down, I'll get the strain. Problem is, if you scroll down, your input will go down also. But my should not go down. That means I made a mistake. What to do? How to make your L not fixed? Just put a dollar sign. If you put a dollar sign before B, then B will not move. But if you put a dollar sign before 1, 1 will not move. So ideally we should put dollar sign only before 1. But if you put for B, no problem. But I do not need it. But I put both, no problem. It's good. Okay. Now if I do that, what will happen? When I will scroll down it, you can see the number says. That means it say here, if I click it, it is actually this number divided by this. This is not moving because I fixed it by put a dollar sign. So dollar means money. If you give money to somebody, they will listen to you. So I gave money to on and told on stay here, do not move. Okay, so yes, if you do not know it, you should know it because it is in AP exam also. In AP exam, you should solve, or in Excel. Excel is very important for AP exam. Or maybe they stopped this portion. Okay, that's a different story. In AP exam, the Excel was in the exam, but nowadays they deleted. Okay, now stress. Equal sign, force divided by area. But I should fix the 3. I can fix B. If you move laterally, I should fix B. We will not move laterally, so no problem. Okay, if I pull it down, and we got it. So many fraction. I do not like fraction, so if I click this symbol, it will be a very beautiful number. Okay, and also it looks everything is at the side. Put it in the middle. Yes. So it is at the middle. Now what how to will do? We'll draw this. So select these two. Make sure when you select, the first one will be in x-axis, second one will be in y-axis. So if it is not, you can rearrange your column. Insert, scattered, this. But I need some line also. Yes, see, I can do this. This one looks better, or even you can take this and clean. But sometimes in engineering, in laboratory report, we like to see the point also. Okay, then done. You can see. Now, do not just paste it in your Word file. No. After cooking, you cannot serve as it is. Serve with a pan. You have to put it in a beautiful dish, put some decoration, salad on the corner, make it beautiful. Yes. How to do? Start title, write something, or I do not write anything here. I will write in below the figure on stress, strain diagram. And what I like to, this color doesn't look like good to me. I'll zip format, and black is standard color. And this marker, I should change the color to say marker option. Which side this marker is popular, this diamond shape. Okay, and put a black. Okay, so black, it looks better now. This outside border, nobody, oh, at least that is beautification. At least write the axis is very important. So click here, um, design. You can simply take different layout, whatever layout do you want. If you find anything here, but I do not use from here. I'm just showing you that you can. As I go to add start element, I write horizontal and I write axis title vertical. So I go here and write stress. Always write the unit. It's very important in all engineering. Never forget your unit. Always strain has no unit, so no problem. And then click here, go to times. It will change the font. Say Times New Roman. Standard. It is kind of not black. Click here on the graph. Take black. See, now it looks so beautiful. At least it's standard. This outer shade, we do not like to see a border here. Right click, format chart area, no line. So there is no outer shade now. Now you can copy and paste in your Word file. See, beautiful graph. Then whatever figure, I know that you will make this mistake in your laboratory again. No figure, no table can can have a, no, cannot have a, I got confused. Actually, every figure, every table must have a name. So right here, figure 1 stress. When you write it, always vertical axis first. Stress, strain, diagram. That is write something. So, and in your body, always cite this. In any technical report, every figure table must be cited in the body. If you do not need to cite inside the body, that means you do not need this figure. Put the figure in the appendix. But if you need the figure, then cite it in the body. When you are writing, at least cite it. That figure 1 shows stress strain. In the diagram, we can see that yield is 60, ultimate is this, from the, something. Again, I'm telling it again. Every figure table must have a caption or title or name, and that name must be cited. Okay, now I think that you can do the homework. I do not need to deeper. And if you do Excel, it is very quick. Otherwise, you have to do every time calculation is difficult. Okay, so I will stop here.